Prove by induction the formula for the sum of the first n terms of a geometric series. That is, prove that for r not equal to 1, a plus ar squared plus as far as ar to the power of n minus 1 equals a into 1 minus r to the power of n over 1 minus r. The first step in proof by induction is to consider the base case. What is the smallest number that n can have? Well, let's look at this series. Sn stands for the sum of the first n terms. So it's a plus ar plus as far as the nth term, which is actually ar to the power of n minus 1. This power here is 1 less than n. So S1 is just the first term. In any series, S1 is equal to T1. So we want to see if the formula is true for n equals 1. That's the base case. Well, S1 we know is A. Now let's see if we get A by plugging 1 into the formula that we're trying to prove. So let's take that formula and plug 1 in for n. So we just replace n with 1. And we see that the 1 minus r's cancel, and we do get A, which is S1. So the formula is true for n equals 1. So that's the first step in proof by induction. The second step in proof by induction is to assume the formula is true, assume true for n equals k, where k is any number greater than or equal to 1. Any integer. Proof by induction only makes sense for integer values. So what's the assumption statement? Well, the assumption statement is that a plus ar plus ar squared plus as far as ar to the power of k minus 1 will equal the right hand side with n replaced by k. So k is some integer greater than or equal to 1. So we're assuming it's true for this integer. The next step in proof by induction is to prove that the formula is true for n equals k plus 1. To do this part, we need to build on our assumption statement. So we need to build on this so we can add the same thing to both sides of this, or we can do the same thing to both sides of it. And you know, if we end up proving the formula for n equals k plus 1, then we're done. So we build on this. But first of all, what does this series look like for n equals k plus 1? Well, we're going to be getting the sum of the first k plus 1 terms. If you like, you can write that as s k plus 1 to indicate we're getting the sum of the first k plus 1 terms. So how do we do that? Well, we go as far as the kth term, which is ar to the power of k minus 1, and then we have to add on a new term. Now I'll do that in red. The new term is got by replacing k with k plus 1. If we replace k with k plus 1, we get k plus 1 minus 1. That gives us k. So this is the sum of the first k plus 1 terms. It's really just going back to the formula and replacing n with k plus 1. In general, you know, this last term would be ar to the power of n minus 1. And we plug k plus 1 in for n, we get ar to the power of k plus 1 minus 1, or ar to the power of k. Now, we're going to build on our assumption statement. So the right hand side of the assumption statement is a into 1 minus r to the power of k divided by 1 minus r. But we're adding this red term onto both sides of the assumption term. So we have to add it onto the right hand side to balance both sides. Okay, so it's like we've taken our assumption statement and added this term onto both sides. So we haven't actually changed it. If we're assuming that this is true, then this here must be true. Now let's take a closer look at this thing here. What we want to do is see if this thing is the same as taking our formula that we're trying to prove, which is Sn equals a into 1 minus r to the power of n divided by 1 minus r, and replacing n with k plus 1. If we replace n with k plus 1, what do we get? We get a into 1 minus r to the k plus 1 divided by 1 minus r. So we want to see if this thing here is equivalent to a into 1 minus r to the power of k plus 1 all over 1 minus r. If it is, then we've proven that the formula is true for n equals k plus 1. So let's see, what can we do with this? Well, we could get a common denominator of 1 minus r, and then we have a into 1 minus r to the power of k. That's just over 1 minus r, that's just the first term, plus, well, to get the next term, this is over 1 if you like, we'll have 1 minus r times ar to the power of k. So you see, if you put this over this, you get this first term. If you put this second term over 1 minus r, the 1 minus r's will cancel and we'll get ar to the k. It's just getting a common denominator. Multiplying a in here, we have a times 1 is a, and then we have minus ar to the k. Ar to the k by 1 is plus ar to the k. Ar to the k by ar to the power of 1 is ar to the power of k plus 1. We add the powers. Two r terms here. So we get minus ar to the power of k plus 1. These terms cancel out. So it looks promising. It looks like we are indeed going to get our formula with n replaced with k plus 1. What we get is, we factorize out the a out at the top, you can see it now. We'll have a times 1 minus r to the power of k plus 1 over 1 minus r. And that's just s k plus 1. That's the formula with n replaced by k plus 1. So this shows that the formula is true for n equals k plus 1. So then the logic of induction takes over. So we said we were assuming the formula was true for n equals k, where k is some integer greater than or equal to 1. So for example, if k was equal to 1, say k was equal to 1, well, we know this is true from the very start. So if the theorem is true for n equals k equals 1, then it's going to be true for n equals k plus 1. Well, in that case, it'll be true for n equals 2. It's true for k equals 1. It's true for n equals 1 plus 1, which is 2. And then, if we're assuming it's true for n equals 2, 2 takes the place of k. That leads us to the conclusion that it's true for n equals k plus 1. 2 in for k, then it's true for n equals 2 plus 1, which is 3, and so on. So it's true for all positive integers. By writing the recurring part as an infinite geometric series, express the following number as a fraction of integers. Here I've written out 5.21 recurring in this form. We just add 5 onto 0.21. That gives us 5.21. That gives us this number to 2 decimal places. If we want this number to 4 decimal places, we would take the first 3 terms, 5 plus 0.21 plus 0.0021. To 6 decimal places, we would take the first 4 terms, and so on. So the pattern is pretty clear here. We're adding in an extra 2 decimal places each time. So how do we do that? Well, we take this number and multiply it by 0.01, or if you like, 1 over 100. So we see that this series is a geometric series. The first term is a, which is 0.21. The second term is a times r. So we multiply 0.21 by 0.01 to get 0.0021. And the third term is a times r squared. If we square 0.01, we get 0.0001, We multiply that by 0.21, we get 0.000021. So that's the pattern. So we multiply each term by r to get the next term. In this case, r is 0.01. So we multiply this by 0.01 to get this term, and to get the next term, we'd multiply this by 0.01 to get 0.21 times 0.01 cubed, and so on. So this is a infinite geometric series. We can just take the 5 out to one side and just look at the part that's bracketed, and note down what a and r are. A is 0.21, r is 0.01. Now we need the sum to n of a geometric series. We saw that in the first part. It's a into 1 minus r to the power of n divided by 1 minus r. The only thing here is that we're interested in an infinite series, so we're interested in the sum to infinity. So what happens as n goes off to infinity? Well, we see that r is a number that lies between 0 and 1 for this geometric series. R is 0.01. So as we raise r to increasing powers, then r to the power of n will actually go to 0. See, r is 0.01. If we raise it to the power of 2, we get 0.0001. Raising it to the power of 3 will make it even smaller. So as n goes off to infinity, r to the power of n will go to 0. So we're going to be left with a into 1 minus 0. Well, that's just a times 1, which is a over 1 minus r. So this is a formula, if you like, for the sum to infinity of a geometric series. Now this is only true as long as r lies between 0 and 1. Or if r is negative, it has to lie between minus 1 and 0. If r lies in this range, then the series will converge also. The series won't converge if r is outside that range. The series will diverge. So the sum to infinity is some number given by this formula. We just drop that term. A is 0.21, r is 0.01. So we have 1 minus 0.01. So we have 0.21 divided by 0.99. So that's 21 over 99. Of course, if you want to check this, you can go to your calculator, take 21 and divide by 99. And we do indeed get 0.21, 0.21, 0.21, or 0.21 recurring. So 5.21 recurring is 5 plus 21 over 99, which is just written 5 and 21 over 99. 21 over 99 can be cancelled down to 7 over 33. So this is the answer. Another way that we could write this as a fraction is to start off with our number and multiply it by 100. So let's call the number x. If we multiply it by 100, we get 100x. So that's going to give us 521.2121 recurring. We just moved the decimal point. Now, look what happens when we subtract these numbers. Something interesting happens. 100x minus 1x is 99x. So what I'm doing is I'm taking this lower equation and subtracting the top equation. 5.21.2121 minus this number up here is going to give us 521 minus 5, which is 516. The decimal part cancels out when we do the subtractions, so that's why I chose to multiply by 100 to make the decimal part cancel out. So x is 516 divided by 99, and you can break that down. 516 divided by 99, so that's 5.21 recurring. So that checks out. Or we can write it as, like before, we can write it as 5 and 21 over 99, or 7 over 33.